So when we have a graph with weights on the edges, so here we have weights, so to travel from A to D has a cost of 1. This might be $1, it might be 1 mile. Somehow this is representing the cost or expense of traveling from vertex A to vertex D. So in this case, there are a lot of different Hamiltonian circuits on this graph. We're interested in the minimum cost Hamiltonian circuit, and sometimes this is called the traveling salesman problem. And the reason is, you can imagine that you have a salesman who needs to visit these 4 different cities and wants, they have to visit every single one of them, but they don't want to have to backtrack. So they want to visit each city and then return home at the end of the day. Okay, so we're going to apply an approach called the brute force method, which does exactly what it sounds like. We're just going to try every single possibility. So let's try a few possibilities here. So one possibility would be to go from A to B to C to D to A. So that was A, B, C, D, A. Right? A, B, C, D, A. So this lists the order in which we're visiting the vertices. And the total cost here would be 4 plus 13 plus 8 plus 1. Right? We add up the cost of each of those legs of our path, and we add those up, and we get a total weight of, or total cost of 26. Now notice that this is exactly identical to the circuit ADCBA in terms of cost, right? ADCBA. It's just the reverse order. And so we're not going to look at both of these, because we know that they're going to have the same cost. So we don't consider these to be unique circuits. And so we're just going to ignore that one. And now let's look at another possibility. So another possibility would be to go from A to B to D, and from D down to C, back up to A. So that was A, B, D, C, A. And that would be 4 and 9 and 8 and 2, and that has a cost of 23. Now I'm going to get those out of the way, because that's starting to get a little messy here. And let's look at one more. There's one more unique circuit here, and that's A, C, B, D, A. Right? This is different than our first one. The first one we went A to B. So this was A, C, B, D, A. So that's 2 and 13 and 9 and 1 has a cost of 25. And so of these 3 unique circuits, and it turns out that these are all the unique circuits, the one that is minimum cost is this one right here. So this is our minimum cost Hamiltonian circuit for this particular graph. And here was what we called the brute force method, right? We looked at every single possibility, and while this will always give us the ideal, the optimal answer, so this is called an efficient algorithm, an optimal algorithm. It is not an efficient algorithm. So this is optimal, because it will always give us the right answer, the best answer, but it is not efficient. And we'll see why in just a second.